So, good morning, everybody. First of all, let me thank Michael and Angeles for asking and inviting me to give this lecture on habitat models and especially on the MesoHABSIM habitat model. I will introduce the general concept of habitat modeling in rivers, which is strictly related to environmental flows. And I will try also to show how the habitat modeling could be used quantitatively and practically in EuroFLOW's assessment. The lecture will be then focused particularly on one specific approach to habitat modeling, which is called MesoHABSIM. And here comes one of the most important concepts of this morning, which is about recognizing the hierarchy and the relevance of spatial scales that are involved in habitat assessment, and to which extent habitat modeling is linked to fluvial geomorphology and to the morphology of the river channels or the river corridors. So this will be the main focuses of this lecture. The slides that I'm using have been prepared mainly by my colleague Paolo Vezza, who is a researcher at the Polytechnic of Torino, and we are part, Paolo, I, and several other people, you will see their pictures, their faces at the ending slides. We are part of a larger group in Italy that is promoting the integrated use of eco-hydraulics, eco-hydrology, and geomorphology tools to quantify EuroFLOWs at a national level, starting from the national legislation, national law, down to the local implementation. So it's a, let's say, no transfer effort, which is backed up by research activity that we are doing on several aspects of habitat modeling. Please do not hesitate to interrupt me if there is any concept that is not clear. From your presentation of yesterday, I realize that some of you may be already familiar with some of the concepts that I'm going to present, but maybe some of you will be less familiar. So I will try to keep the level very broad and so that everyone can follow, but please, if someone is lost, just raise your hand. So, the general context related to EuroFLOWs and habitat is probably something that you are already discussing in the course. There is some evidence, some studies that indicate that at a global level the decline of biodiversity and the loss or the risk of losing species is higher in freshwater ecosystems compared to other ecosystems. And here are some examples of endangered species, especially in our context, in a European context. And the decline, I mean, one of the main reasons for associated, which is believed to be associated with the decline of freshwater species, are what are so-called hydro-morphological alterations. So this is the first important concept because it's strictly linked to habitat, to river habitat modeling. I'm showing here some examples of what can be, what can fall in a general category of hydro-morphological alteration. What I mean with hydro-morphological alteration? I mean alteration of the hydrology, the hydraulics, and the morphology of a river system, of a river corridor, at multiple scales. And of course, we have different types of hydro-morphological alterations in river systems related to the use we do of rivers. And so some examples are very simply speaking, dams and every type of impoundment that is imposed on river system, which are on the other side, of course, very useful for flow regulation and many production activities. Then we have, in a more general way, water abstractions. So there are water abstractions that do not require a reservoir, so do not require a dam, maybe require a check dam, but abstract water into a reach of a river system and then give the water back further downstream. Other types of hydromorphological pressure are related to, let's say, the engineering of the river channel. So we have levee construction, construction of check dams, mostly built for flood safety purposes, for hydraulic safety purposes, and this type of hydromorphological alteration may limit, for example, the lateral mobility of the channel, may reduce the morphological complexity of the channel if, for example, channelization often implies narrowing or have implied narrowing. But these are not the only ones. A very important form of hydromorphological alteration, for instance, is sediment mining. River sediments is a very cheap material for whatever type of construction. So especially now, especially in emerging or developing countries, there is a strong tendency of increasing mining of sediments from river channels, because sediments is readily available and has a lot of market when it can be sold. And this was very also common, for instance, in Italy and in Europe from the 50s up to the 80s, more or less, in which also there was very little regulation about how sediment could be mined. And why I'm saying this is a hydromorphological regulation, because it has important effects on the channel morphology, and it has been shown in many river systems, in Italy, in France, but everywhere in the world, that intensive gravel mining often implies incision of several meters sometimes, of long reaches, of long stretches of river systems, and also narrowing. So a change in the channel morphology, and so a change also in the habitat. I'm not sure if you already went into the legal framework at the European level, but so the first important frame in which we discuss about habitat models is hydromorphological alteration. So because when we study the physical habitat, one of the fundamental descriptions of the habitat is the physical part, which is related to the flow of water over a channel morphology. So it's strictly related to hydromorphology. It's not the only part, but hydromorphology is a very relevant, very important component of the physical habitat in rivers. Then the legal framework. At the European level, there are several directives that are related to the stress the importance to protect and quantify habitats, in this case with the Habitats Directive for many different environments, not only freshwater environments, but of course it has strong implication for the freshwater environment as well. We have the Water Framework Directive, of which probably many of you are aware of, which is the, let's say, main legal umbrella that indicates the EU policy in terms of protection of water-related environment and water systems, surface, subsurface, coastal, and so on. And there are other directives that maybe are not strictly focused on habitat conservation or river quality or the environmental quality in rivers, but which have important implications. For example, the EU Floods Directive, which is the framework directive for flood protection in Europe, urges European states, member states, to take a series of action to ensure that river systems are less and less risky in terms of floods, in terms of, let's say, hydraulic safety. And this implies the need to undertake mitigation measures to flood risk, prevention measures, and of course, so in the end, they imply to act on the hydro-morphology of the river to increase the safety of human activities and human population. So it has implication also on the habitat. And one of the main debates that is now active in many states is how to reconcile the requirements of the Water Framework Directive on one side and on the Floods Directive on the other side, because sometimes at a local level, when it's about implementing them, you might have some conflicts. You might have the need to increase let's say, to artificialize, to engineer more the river channel to satisfy requirements of the Floods Directive, but on the other side, you are reducing maybe the habitat quality. And so an interesting open area for research and for experimentation is to find win-win solution and trade-offs between the two requirements of the two directives. So, after this general framework, so what I mean with hydromorphology and hydromorphological alteration and the legal framework, we now enter more deeply into the habitat modeling concepts. So how, first of all, which are the possible applications of habitat modeling? So we stressed mainly three possible applications. One is clearly directed, clearly focused with the topic of the course. So habitat models could be used as part of assessment methods to determine EuroFLOW requirements in a given stream. A second application is not on the planning phase, but is on the assessment phase, on the evaluation phase. So habitat models could be used to assess the impact of existing or new type of hydromorphological alteration. So whatever is changing, is affecting the hydromorphology of a stream, could be a dam, a gravel mining, even a river restoration project that aims to improve the river quality, or a dam removal, or what is happening in some states. Habitat models offer a tool to assess the impact of these measures. Habitat models can also be used to assess the effect of other type of measures that are maybe more targeted to improve the environmental quality, to promote the conservation of some threatened species, of endangered species. So I think these are three broad categories of application of habitat models. So a third concept after the framework, the initial framework, is I want to introduce. I will repeat. I will stress this concept several times during the lecture. Is the relation between habitat modeling and habitat in rivers and fluvial geomorphology. Why I would like to stress this element? Because the habitat of a river has been created by a series of processes, especially physical processes, not only, but let's say biophysical processes more in general, that act at a different set of spatial and temporal scales, and that shape the river morphology as we see in one time, and which is not a static element. The river morphology, depending on which river and which condition we look at it, is generally speaking a dynamic element. Some rivers are much more dynamic. Here in our region, in the northeast of Italy, we have several braided rivers like the Piave, the Tagliamento, which are still quite active and dynamic. They change their morphology quite frequently. Some other rivers are much more static, either because they are regulated or just because of their environmental setting are very move and change their morphology at a very slow time scale. But overall speaking, river systems are dynamic elements and change their morphology, especially under the action of the hydrology, so under the action of a given hydrograph of floods, which determines sediment transport, which implies that some sediment is taken away from one part of the river and is deposited somewhere else in the river. And this creates different shapes, different forms, and in the end, different habitats. So, in this slide, we have let's say, a view of what can be called the hierarchy of spatial scales at which different geomorphological processes occur, and we are interested in understanding which is the spatial scale at which we should look when we think of river habitat. So, let's say we can start with a very broad spatial scale, which is a region, which can include, which is the region, so which can include many river catchments, maybe a homogeneous region. Then we move to the smaller spatial scale, which is the river catchment, which is the natural, let's say, unit at which all processes related to, let's say, surface water resources occur. Then, of course, in a catchment, we can have different physiographic unit. In the north of Italy, where we have the Alps, bordering with Austria, Slovenia, Switzerland, France, and so on. We have surely an alpine physiographic unit in many river catchments. Then we have a pre-alpine physiographic unit, which is different because has a different flow regime, has a different lithology. Then we gradually move to floodplain areas, which are a different physiographic unit. So there are portions of the catchments which are clearly different from a geographic point of view. Then inside each physiographic unit, we can distinguish river segments. So quite long stretches of river that have, like what we see here in the picture, that have more or less homogeneous characteristics in terms of sediment supply or hydrology. And an example of a river segment is visualized in this image you see on your left. And the red boxes identify smaller units, again, which a group of geomorphologists have decided to often call reach. So a reach is also homogeneous in terms of the channel morphology. You see, for example, number 1 is a reach that has what is called a pseudo-meandering or nearly meandering behavior, and it's pretty much homogeneous in terms of its morphology. So we have underlined the reach because the reach is very close to where the habitat of many biological species, and now we are keeping it very general, so we can think in terms of habitat for vegetation, whatever refers to vegetation, to fish, to macroinvertebrates, even to the smaller organisms like diatoms and so on. And we are trying to look at which is the correct spatial scale, or which are the set of spatial scales at which we should look to assess habitats. Why this is so important, I think, is because the morphology of the reach, so the habitat structure that has been created at the reach level, depends on a set of geomorphological processes that also act at the catchment, at the physiographic unit, and at the segment scales, and sometimes have different processes. Of course, the higher the spatial scale, also the longer is the time scale of the geomorphological processes that we are looking at. If we say at the catchment or regional scale, we are speaking probably in terms of geological spatial scale. But if we go down to the reach level, we have processes that can be much shorter. For example, at the time scale of one single flood event, which can completely change, in some cases, the morphology of the reach. And now we go into the most interesting part for habitats. So this could be an example of a reach, which is quite homogeneous. We have riparian vegetation on the sides. We have gravel bars, a series of gravel bars that are more or less alternate in the left and right directions, and we have a series of wet units, we have pools, we have some backwaters, we have probably some riffles and some glides, so some different units. And when I say unit, I'm now moving to the smaller scale, to the lower level, and which is the geomorphic unit. So we can think of this reach here in this picture as a superposition of different geomorphic units that are homogeneous at a smaller scale. For instance, here we have what can be called a riffle, and this area is somehow homogeneous in terms of bed material properties. We have a similar distribution of stone, cobble, and pebble sites. Water surface properties. We have a lot of whitewater foam created by the hydraulic jumps. The slope of this unit is quite homogeneous, and these characteristics are clearly different from what you imagine is starting here, and also from what is the upstream geomorphic units. So we can visualize a reach which is homogeneous in terms of morphology as a mosaic of different geomorphic units that are units at a smaller spatial scale that are also homogeneous and different from each other. And the descriptors of these geomorphic units, just looking then visually, could be related to the bed material, the size of the bed material, the property of the water surface. Here it's much more flat, and here it's much more with waves and oscillating. The slope, the local slope here of the riverbed is higher compared to the local slope there. And maybe, if we then get wet and we enter into the river, we could detect that some geomorphic units will have aquatic vegetation in them, some others do not, maybe because the vegetation cannot stand higher flows, so the velocity is probably also different. And I'm now using these descriptors to make the concept hopefully clearer. And these descriptors are also the descriptors of the habitats where many species are living. So for some species, the geomorphic units, especially, for example, for fish, has been recognized to be the relevant spatial scale, because a fish is often looking for, is moving because of also of its dimensions and its, let's say, life cycle stages, is moving in the streams and may have some preferences in terms of these descriptors, in terms of velocity, in terms of depth, substrate, and so on. And but other organisms may prefer a different spatial scale, or may actually we should look maybe at different spatial scales for habitats related to other organisms. For example, inside a geomorphic unit, we have a set of smaller hydraulic units, which are also homogeneous and maybe a bit different between different parts of the same geomorphic units, and this is what is called an hydraulic unit. And finally, an hydraulic unit is composed by river elements. If you do measurements in a river, and maybe some of you already has practice in it, you may see that there are distribution of some invertebrates, even within a single stone that is below water, and that form distinct patterns of the use of that very small habitat. So I try to summarize this first concept related to habitat modeling. So there is a very strict link between what is physical habitat in rivers and let's say geomorphological processes. And because geomorphological processes occur at a very wide set of spatial and temporal scale, it is very important to keep the two, let's say, the two information together. So far we haven't speak really too much about habitats and about the biological part, about the species preferences. I'm starting, especially framing the broader context from a geomorphological perspective. Starting from probably the early 1900s, and then especially from the 1950s, with very famous geomorphological work from Luna Leopold, Gordon Wallman, and many others who followed. There have been many, you'll find in the literature many proposals, many schemes that classify the channel morphology, the morphology of all rivers, basically, you can find in the world. And there is a quite general agreement of which are the main controls on the channel morphology. Not everything is really understood, but this is one example of a fluvial morphology classification in which we have some, let's say, controlling factors like the bed material caliber, so the size of the bed material in the vertical axis, and different types of channel morphology that can develop, that are observed to develop with different bed material size. The vertical line discriminates between, let's say, steep streams, mountain streams, for which we have this typical channel morphology, depending if they are confined or semi-alluvial or not confined by, let's say, lateral valley sides and so on, or rivers that are fully alluvial and laterally unconfined. So they're, let's say, free to choose the form they prefer. And depending on the setting, let's say, especially two main variables, so the flow regime, the hydrology of the river, and the sediment supply regime, and of course the slope of the valley, so the environmental conditions, the type of climate and the type of riparian vegetation, a river can develop many different types of plant forms. Could be fully braided, braided with islands, anastomosing with vegetated islands and channels moving between vegetated islands, could be meandering or pseudo-meandering, could be almost straight or sinuous, could have bars, could have less bars. And so understanding when looking at habitat models, and especially when looking at many regulatory frameworks, like the EU Water Framework Directive, that indicate some reference conditions, which should be the ideal condition without anthropic pressures. It is very important to first identify which is the natural tendency of your river towards the channel pattern. So which type of pattern is the river creating? You can imagine that a braided river, which is a river with many channels that bifurcate and join together and bifurcate again and create many different bars, will have a different structure of habitats, of geomorphic units, compared to a meandering river in a very low slope environment with predominant fine sand, silt and clay, with cohesive sediments. So that the type of habitat and also the maximum potential in terms of habitat will be very different from the two types of rivers. And so I'm now concluding this first, let's say, conceptual important point about the link between fluvial geomorphology and river habitat with these slides, which I hope, let's say, summarize the importance of understanding what is the natural tendency of the channel pattern, because this controls the morphology at the scale of the reach, and inside the reach we will have a different assemblages, a different mosaic of geomorphic units, which are the, let's say, the fundamental habitat unit, especially for some species, let's say, for fish at least. Do you have any question on these first concepts?
Okay, I will go ahead. And now we enter more in detail into habitat models. So this is a very classic slide. Let's think in terms of what habitat means. I think yesterday with the cocktail we had a very good example of our habitat. We were on that side of the terrace with a lot of sun. It was very hot, and well, there was good food, so food was there, and we stayed there eating and drinking, but people were starting sweating. I was a bit hot. Then we said, okay, let's go for a photo. So we crossed this, and everyone coming inside said, oh, now it's very cool, that's much better. And we stayed on this side of the terrace. So let's think of the two sides of the terrace as two geomorphic units. Of course, we could stay in the other geomorphic units with the sun where the food was, also especially because there was food. But we were much happier probably to stay for a while in this part where there was more shadow, fresh air, even if the food supply was less. So this is to say that habitat models are modeling the habitat, are not modeling our behavior or the behavior of a species inside the different habitats. So if we move to aquatic species and to rivers, the descriptors of the habitat can be somehow similar to what we use to describe our habitat, like temperature, for example, is a fundamental driver. Also light. But in rivers, we have several hydraulic descriptors, like depth, like velocity. Several, I mean, when you start to have velocities higher than 1 meter, 2 meters per second, then many species will not be able to stand in those velocities. But we have not only physical characteristics. A river channel, now I'm narrowing the concept of habitat models into the wet geomorphic units, so below water, aquatic habitats, not terrestrial habitats or riparian habitats. But we will have some species can find a refugia or shelter between some aquatic plants or behind some big boulders that create wakes and reduce the velocity. Many fishes for spawning look for a quite narrow range of bed material because with the movement of their body, they can create some holes. They put their eggs inside, and it's also important that there is not much very fine sediments because these eggs has to keep oxygenated, so water flux between the surface part and the subsurface need to be incentivated, or there need to be connectivity. So depending on the life stage, when it's in a spawning life stage or in a young life stage or an adult life stage, different species may prefer different combination of these physical and biological, so let's say biophysical variables or descriptor of the habitats. So the challenge of habitat modeling is to provide a description of these, let's say, environmental conditions. And it's an important concept that this, we can view this as a necessary condition in some way for some species to be found in a certain place, but not a sufficient condition. Because, for example, we can have a perfect habitat here for a given fish, but if a predator of that fish is present, probably the fish will avoid that area. So we should not be surprised if in some cases we have, from our habitat modeling exercise, an optimal habitat, but when we go into the river, we don't find any of the fish for which we have modeled the habitat. Because the actual presence and the actual use of the habitat is conditioned by the environment, by the biophysical characteristics of the habitats, but also by other factors that are related to population dynamics, prey-predator mechanism, food availability, which are presently not routinely included into habitat models. In the example of yesterday, some other concept may come out. So we can say that the habitat, in terms of the temperature habitat of this side, was quite suitable, I think, for everybody of us. The temperature habitat of the other side, where we had the cocktail, was not so suitable. But we could stay there for a while. We stayed there for maybe half an hour, maybe 1 hour. Then, of course, the condition changed. But we could tolerate those conditions for probably 1 hour, 2 hours. But of course, if we were asked to stay, to tolerate the same condition, the sun coming, for 48 hours, maybe this would have been much more critical to us, especially maybe in the absence of something to eat. So what I'm saying is that the temporal dimension is very important into habitat modeling, in the sense that species can tolerate some stress condition for a given amount of time, but not for a too long amount of time. So we will come back to this concept in the end when we will see the concept of habitat time series. So time series of the available habitat for a given species. Because, so what is important to remind and to keep in mind is that unsuitable habitats on the other side doesn't mean that you will never find a species there. You may find it because a species can tolerate unsuitable condition for a given amount of time, but not for too long. So the duration, the continuous duration of some particular habitat condition is an important descriptor to be taken into account when using habitat models for, let's say, environmental management purposes, EuroFLOWs, impact assessment, conservation action, and so on. Okay, and now, I'm moving to this slide, which is a very general slide about whatever type of habitat model. So the basic principle of habitat modeling is to put together two elements to derive an assessment of the habitat condition. The first element is the description of the hydro-morphology, so of the hydrology, the hydraulics, and the morphology of each. So let's say of the physical characteristics. One may say, well, maybe of some biophysical characteristics, because vegetation, aquatic vegetation, riparian vegetation may also be important as an environmental description. But most habitat models start from this concept. We describe in any way, with field measurements, with models, with hydraulic models, morphological models, the physical template. And if you see, this is you can view this idealized ridge that is here as really a ridge. So the spatial scale is often, this one is a homogeneous ridge with different units. Then we need a second crucial ingredient that expresses what species prefer, which type of environment species prefer, like in the example we said I was discussing before. So this is a very basic habitat suitability criterion. Is saying that is expressed in terms of a suitability index. You see on the vertical axis we have numbers from 0 to 1. 1 means very high suitability, 0 means no suitability at all, and the colors reflect this suitability. So in this particular case, the optimal depth range for this species is between 100 and 150 centimeters, so it's the green part. But you see the description of this species cannot stay in, let's say, locations where cannot stay at all below 10 centimeters of depth, can tolerate maybe for a little while depths between 10 and 20 centimeters. So if we put together this information, you see that here we have a hydromorphological quantity, it's depth. If we have the information of how depth is distributed in space along the ridge, along our, let's say, morphological unit, at the scale at which, at the geomorphological scale of interest, then we can transform this map of water depth into map of water suitability. Because where we have the deep areas, see the darker blue in the image, we have the green areas, so the most suitable areas in the reach in terms of habitat, because we can combine these two information. So this is, in a very simplified way, but the basic concept of how habitat models are built. Describe the environment, describe the preferences in terms of the same variable that you use to describe the environment, and then put together the two information and derive a map of how suitable your area is. So here we introduce the second dimension. Before I mentioned the temporal dimension, so how it's important that suitable condition or unsuitable condition can be tolerated for a given time, for a continuous duration of time. And the spatial dimension is also very important, because in a given river reach, you can have a distribution in space of more suitable and less suitable areas. So, there are many tens of habitat modeling approaches. As far as I'm aware, but you may be aware of previous information, the first, let's say, relevant attempt to model habitat started in Colorado, in Fort Collins, from a group from the United States Geological Service, from USGS, in the early 1980s, and developed this model, which is called PHABSIM, which I think stands for Physical Habitat Simulation Model or something like that. And this model has found a huge application worldwide. It was the first, and it was based on the same principles that I was recalling before. So the hydro-morphology was described in a very classical hydraulic approach, so through transects of the river, of a river reach, where you would measure the environmental descriptor of the habitat, so velocity, depth, and substrate especially. And then from a set of curves, especially you have here suitability curves in terms of depth and velocity for a given species. So if you remember before, we had in this slide, we have a habitat, let's say, a suitability criteria in terms of depth, and here we have the typical habitat model that has a suitability criteria in terms of depth and in terms of velocity. In some way, these criteria are combined, because you can think of a given point where you have the measurements in your cross-section, you measure the depth, 1 meter, you measure the velocity, 0.5 meter per second, then you go to your diagrams, okay, if we have 1 meter of depth and we have 0.5 meter per second of velocity, then what is the suitability? We need to combine the information of the two curves, and there are different ways to combine them. You can multiply, you can take the minimum, you can take an average. There are different ways to aggregate. The important thing is that here we have, let's say, a univariate description of the preferences of a given species. Here statistics comes to play in a very important way. You can think of those curves as probability curves in some way, because it's more probable that that the fish will use, or the species will use, the area that is most suitable. And so you have a univariate probability relating the probability of use or the suitability with depth, and another curve relating it with velocity. But of course, the species do not think in terms of univariate preferences, but took all the environmental characteristics into account. The result is, of course, a map of habitat suitability, spatially distributed, but you can then, let's go back to the previous images, which is probably easier to exemplify. So we can calculate how much area in this channel is actually suitable for the fish. So we have the total wet area, which is the colored area, but not all of it is suitable. For example, this red part and this dark orange part are not so suitable, but the green part are very suitable. So here comes in the concept of oh, well, I wanted to write, but do we have chalks?
It's not a yellow. It's on the chalk.
Oh. The concept of weighted usable area. Which is, you often find the acronym WUA. So, the weighted usable area is the area that you obtain by summing all these areas with equal suitability and giving each of them a weight that corresponds to the suitability level. So, the green areas will almost weight 1, but the orange areas will weight probably 0.3. So, the weighted usable area is always less than the actually wet area. And if you repeat this exercise for different flow stages, for different discharges, then you can obtain, at every discharges, horizontal axis, the value of the weighted usable area. So here we have these points indicate the value of the weighted usable area that you obtain by increasing when you increase the discharges. Very often these curves, which are called habitat rating curves or habitat discharge rating curve, because they relate the available habitat for a different, for a given species with the stream flow, with the discharge that is flowing in that reach. These curves often have a maximum, so there is a range of discharges that are optimal for that species. Of course, you can intuitively think why this curve has a maximum. If there is zero flow, there is zero habitat. This is trivial. But if we are in a flood, the usable area for most species will be very, very small as well. So the curve will tend to be very low values of the usable area for very small and very high discharges. So there is very likely a behavior with a maximum, with an optimal range.
Sorry, the ADV is the same as the W?
Yeah, sorry, yeah. I think it's area disponibile ponderata, which is the Italian, it comes from some Italian, yeah. So this curve is very is very useful in many cases because if you have flow time series, so if you have information on the hydrology of the stream, so if you know the flow regime quantitatively, and this is often known for many streams where you have flow gauges, then you can convert your flow time series, stream flow time series, into habitat time series. And you can analyze how much habitat is changing in time, and you can determine stress events, ideal events. And if you change the flow time series, because of water abstraction, regulation, or whatever, you will result into a modified habitat time series. And you can compare how the habitat events in time change between a reference and a regulated scenarios. But we will be back to this point later.
The weighted usable area is taking into consideration the depth as well?
Yes, because it is computed with, so potentially you can compute it with taking account all the physical parameters that you use to describe the physical habitat. So velocity, depth, even temperature, the size of the substrate of the sediment, the presence of refugia, of cover, of let's say big boulders, of large woody debris which could act as shelter. So, and you can use it if you have established in some way a relation that expresses the preference of the species you are interested in with respect to those environmental quantities. So you need what is called often a biological model or a habitat suitability model. There are many ways to develop a habitat suitability model.
I just saw from the second, from the first graph on the left, that is like averaging or combining the velocity and the depth parameters to make this weighted usable area.
Exactly.
But it's like on a different depth that we combine the velocity and the depth. So it doesn't have to be like on a single layer of the river, but on many.
Well, in the original version of the PHABSIM, the description of velocity and depth was made on cross-section. So you didn't know what happens between cross-sections. So taking the measurement of this cross-section, then you somehow assume that this description is valid for until the next transect, and so forth, and so on and so forth. So you can get suitability values to different, let's say, stripes of the river, because you need to describe the hydro-morphology. This was the first version. Then this has been improved and modified. We'll go back to how habitat modeling concepts have been evolved. Did I answer to your question?
Just what I don't understand, if it is like averaging the different depths into one surface area.
No.
If it's summing up,
no, it's a local information. Here it's a local information. So for every, let's say, portion of the river for which you say, okay, I'm measuring 1 meter of depth. And here I'm measuring half meter. I need to, okay, my measurement is a point measurement. And I need to extrapolate for which area this measurement is representative, of course, because I cannot measure everywhere, in every point, with a very fine resolution. But a possible way a different way to describe the hydromorphology is working at the mesoscale, so at the scale of the geomorphic units, and working statistically instead of more deterministically. But we will go to this in a short while. Other questions?
Does this model take account also of the different life stages of a species, or just one?
In habitat modeling, the biological models are usually built for different life stages. So for young of the year, adult, spawning, very specifically, there are few models for spawning, but actually different life stages have different preferences, so you need to have different biological models. This was already commented. So what happened is that in some contexts, especially when the geomorphology is quite complex, when the morphology of the leach is quite complex, describing the hydromorphology through cross-section is a bit, you can understand, is a bit limiting. Or if you go in a situation where also the cross-section, like in steep mountain streams, is not really representative of the rich morphology, and so at the spatial scale that I was stressing before. Maybe in some type of rivers, cross-sectional measuring can be a little bit more representative, like in this case. As I said, PHABSIM was the first. Then almost every country and every research group in every country developed their own habitat models adapted to local characteristics. So there are tens and tens of habitat models. A model that is very much used, especially in the German-speaking world, is called CASIMIR, and is modeling the preferences of species. So it's describing the hydromorphology using especially hydraulic models. So water depth and flow velocity come from a hydraulic simulation. Some of you may be familiar with some hydraulic models like HECRAS or Flow2D or Delta3D or Basement. For those of you who, is any of you who doesn't have a clue of what an hydraulic model is? Or you have this basic concept? Well, basically, it's a tool, it's a software tool that is based on the mathematical solution of the differential equation that govern the physics of water flow in a stream, and that if you input rich morphology and stream flow condition, it is able to predict, with a given uncertainty, the depth and velocity field in that reach. And so this is very, let's say, cheap to be used because it avoids long and time-consuming measurements. But of course, for example, we don't have state-of-art hydraulic models that are able to reliably predict how the substrate size changes in a river reach. The state-of-art models, well, there are models that do that, but we cannot really rely. The uncertainties are still too high. So we still need a survey to map the spatial variability of the substrate, at least with some coarse resolution. And the CASIMIR model is famous because it was able to, it used a special technique which is called fuzzy logic. Fuzzy logic is a statistical technique that is able to translate qualitative information into a quantitative values, into numbers. For instance, and this is very important because it allows to develop biological models from expert knowledge. You go into a river, you have local fish experts, you ask how suitable, which are the preferences for which type of species we can find here, which are the preferences, and often this knowledge comes in terms of, let's say, qualitative information. So when water depth is high and flow velocity is low, then suitability is high. This is not numbers, but fuzzy logic is a technique, I will not enter into the detail, that allows to translate this information into a value of suitability between 0 and 1. So translates qualitative information into quantitative information. And so this has been one of the main advantages of this habitat model because it can, it helped developing, in a also a cost-effective way, biological models for many species in many streams. And in some application, the result is very, very similar to what I showed before. So maps of more suitable blue and less suitable purple area. And then I'll move to the MesoHABSIM, which is the type of approach to habitat models that have been developed since, I think, 15, 18 years by a guy. His name is Piotr Parasiewicz. He's a Polish, but he has been for a while working in the United States. And he and his group started thinking in terms of what is the spatial scale at which we should describe the hydromorphology. So let's go. Now we have presented some concept of habitat modeling, have seen some example of habitat modeling, and at the beginning I was stressing so much the importance of the different spatial scales created by geomorphological processes. So you have a fish in the blue part, or a given species, and so what is actually determining the fact that the fish or the species is in a given position? Is it the depth and velocity or the environmental condition in that small squared area around the fish? Is it the neighboring areas, so the red areas around the fish? Or is it environmental conditions that actually occur at a larger spatial scale? Actually, rivers do not look like this, but probably when a fish is moving, the situation will be more still idealized, but like this. So there will be some areas more suitable, surrounded by other less suitable areas, but there will be quite a lot of variability. If you think of your experience in seeing a river, I think everyone has an experience seeing a river, and some of you may have already experience of field work or doing work in a river. You have in mind how much heterogeneous the flow velocity, the depth field, the distribution of the substrate is actually in a river. And actually this variability is hard to be described in a deterministic way if you go at a spatial scale which is relevant for a given species. So we need probably some statistical description of the whole environment. Allora esitali. So the concept that is behind MesoHABSIM, or the let's say habitat modeling at the mesoscale, is this. For many species, the geomorphic unit, which we discussed before, is the, let's say, so that homogeneous area, rather homogeneous area of bed substrate, slope, let's say biophysical properties, is the, there is some ecological research that shows that fishes preferentially move within these homogeneous areas, which spatial scale is settled by, let's say, something, the spatial scale that is hierarchically just lower than the reach scale. But the conditions in that, the hydraulic and environmental condition in that geomorphic unit will be actually variable from point to point. So the main concept behind MesoHABSIM is to describe the hydro-morphology using those geomorphic units as the fundamental reference, and then describe statistically the distribution of depth, of substrate, of velocity within each unit, and separating each unit, each patch. I hope the next slide will make the concept a bit clearer. So, description, habitat modeling, hydromorphology, biological modeling, and habitat models. At the mesoscale, what I mean. So this is the Noce River, field trip number 2 of Friday. We did some habitat modeling in this reach, and these patches, these color patches you see, are the geomorphic units, so homogeneous units. This is probably what is called a glide. If I remember, this is a rapid, this is another glide, here we have a pool. We went into the field and we mapped with a rangefinder, a simple, like a simplified version of a total station. So with the topography measurements, we mapped the contours of the geomorphic units we identified in the field. And so within each geomorphic unit, which we call the mesohabitat, because the mesoscale is what is associated with the geomorphic unit scale, inside each of these, you then describe the environmental descriptor of the habitat, velocity, depth, substrate, and so on, in a statistical way. Many other habitat models were based on a microhabitat scale, because when you measure or you simulate depth and velocity, let's say with CASIMIR, for example, you assign a suitability value for each small area, for each point. If you have velocity simulated with a hydraulic model, you have the size of the computational cell at which you obtain the value of velocity. And if you go back to here, we have some pixels are suitable and some nearby pixels are not suitable. So this is the concept of a microscale description. The mesoscale description will provide an information of suitable or unsuitable, which is unique for the whole mesoscale, for the whole mesohabitat, for the whole geomorphic units. But let's visualize some of them. So, typical example of geomorphic units of mesohabitats would be a pool, that you see here, then there are different subtypes of pools. We have a dammed pool, which is created by maybe a log jam, or a meander pool that is created by the erosion and sequences of bars and scours in a meander bend. Then we have a glide, which differs from a pool because the water is running. The riverbed is more or less flat and doesn't have a counter slope in the end. We can have riffles, which are bits with more slope and more wavy water surface. So a recent innovation that has been made, especially in a quite large European project, which has been called REFORM, it was about hydro-morphology and ecology, was to provide a clear taxonomy of all these geomorphic units so that they can be objectively described in the field and not, let's say, subject to arbitrary judgment. Yeah, so this slide, let's say, summarizes this link that I was mentioning between the geomorphic units and the mesohabitats, and broadly speaking, between fluvial geomorphology and ecohydraulics. And you can find in the website of this reform project all the, let's say, taxonomy of the geomorphic units and how they are related to mesohabitats. So what is a pool? How can you recognize a pool in the field, or a cascade, or a rapid, or a riffle, or and so on. And this is a paper that describes this with all the taxonomy. So GUS stands for Geomorphic Units Survey. I may write it because I'm not sure it's written in the slide. Let's visualize these geomorphic units a little bit more. So, actually, in a more subtle way, we can have macro units, which could be, let's say, the wet channel is a macro unit. The riparian units can be a macro unit. The terrestrial habitat, the floodplain areas are macro units. Inside these macro units, each macro unit is composed by a unit, which is actually what we call the mesohabitat, if it's wet. And all the units that are inside the wet channel could be riffles, pools, runs, glides, and so on. And then, of course, we can have subunits, which are portions of smaller portion of the large units. Okay, let's go a bit faster to see how the habitat modeling concept that we showed before is translated when we work at the mesoscale, so at the scale of the geomorphic units. So we need to provide, in some way, a hydromorphological characterization of every unit. In that image, you see the patches correspond to both dry and wet units. If we speak about fish habitats, we are interested only in the wet units. We need to have some biological model that expresses species preference at the scale of the geomorphic units. We add the temporal component, so the flow regime, a hydrograph, the time behavior of the stream flow, and then we define the variability of available habitat in time and space. So, this is in another stream. All patches with different colors are the geomorphic units, but a biological model has been applied. So, red units are unsuitable, green units are optimal, and yellow units are suitable. So we have 3 levels of suitability, not anymore a continuous level, but the model, the integration of hydromorphological description and the biological model is saying that the suitability, how the suitability is changed unit by unit, not cell by cell, let's say point by point. But from this information, you can still build a weighted user area, and so a discharge habitat rating curve. If we have the description of these units, how these units change it with the flow, then of course we have a description of how the habitat changes in time because of flow variability.
Actually, according to a fish, is it really representative of all the species in the aquatic environment of the river?
You mean if the fish is representative of all the species?
Yes.
Oh, no, of course not. I mean, depending on the target of of your application. I mean, habitat models is not the whole story, of course, and they are built. All habitat models require a description of the suitability for a given species and for a given life stage. Then it's more, let's say, a management choice to select, in every case, which are the species of most of key interest, and if it's fishes, if it's plants, if it's invertebrates, which type of fishes, which type of, and of course, in principle, you can build habitat models for vegetation, aquatic and riparian.
So it doesn't coincide with the interest of other types of species?
Let's say that there are several ecological studies that say that choosing some fish species for assessment of habitat also provide a good ecological, good representation of the ecological status of a stream. But of course, it's not the whole story. Fishes are into, let's say, I'm not a biologist, but they are part of the trophic chain. So if the river environment is in a good health for some target fish species, we can assume that it's probably a good proxy for also other ecological processes, but not for all, of course. It's not. Then the biologist will have to comment more on this because I'm not a biologist. Okay, I will go a bit fast now on the technicalities. So how you describe the geomorphic units, how do you describe the preferences. But basically, geomorphic units are usually described by field surveys. So use topographical instruments like a rangefinder or a total station, or you can even use a drone to map the units. But then you have to get inside to measure velocity, substrate, or to estimate all the habitat descriptors. You can use remote sensing. So this is an image taken from drone. Even aerial images. You can use mathematical models, hydraulic models, especially in cases where you cannot wade into the stream, into large rivers, or in non-wadable condition. You need to complement different techniques. This is, for instance, the topic on which David is doing his research, how we can use hydraulic models at the mesoscale to describe patches of homogeneous units from hydraulic models. This is the use of hydraulic models at the mesoscale is still a matter of research. And then you need to provide models of the biological models. So there are different ways to build it. The way that it is most used in the mesohabitat approach is to isolate the mesohabitat. If you want to build a model for, let's say, we have Salmo marmoratus, is the marble trout, is the endemic species in the south of the Alps. It's very important. It's a target species for conservation and so on. So how do we build a model of the preferences at the scale of the geomorphic unit? What is done normally is to isolate, you see with nets, every geomorphic units, to go with electrofishing so that you collect, you measure, you weight, and you describe all the fishes that you can sample in the unit that was occupying the unit. If you do it for many units, say 50 or 80 units, in different streams, in different conditions, in the same, let's say, geographical region, then you can end up with a multivariate statistical model that says the probability of absence, of presence, or of abundance, depending on the whole set of environmental descriptors of the habitat. So in the MesoHABSIM approach, most models are built like this, starting from a large number of observations that relate the amount and type of fish that have been observed in a given habitat with the hydro-morphological characteristics. And then, once these multivariate statistical models are built, they are used to feed the second part of the habitat models. So these are some representation of these biological models. They can also be made from literature with conditional models. And you end up with this type of description. You see the value of discharge here is 400 liters per second. The geomorphic units have been mapped. The biological model has been applied. Then you have another mapping at 1.4 cubic meter per second, and you have another spatial distribution. 4.4 meter per second, you have another spatial distribution of the suitability. So in this way, you can end up with the results of the habitat flow rating curve for different species, different life stages, and of course, this curve can vary depending on the hydromorphological condition, on, let's say, processes like armoring of the riverbed, channel narrowing, incision can reduce the available habitat. Other processes can increase the available habitats, like increase of connectivity, fish passes, habitat improvements, and so on. And now the last concept. We have the habitat flow rating curve, and we want to use this information for management in some way. So how can this be used? I illustrate how this has been derived in some cases from MesoHABSIM, but it's common for all habitat models, because all habitat models end up with a relation which is WUA against discharge. That is typically a curve with a maximum. So here we have a stream flow time series, or discharge time series. I use discharge and stream flow as equivalent words. We have several years, and I use some mathematical notation. So let's say the stream flow series, we can indicate it as Q as a function of time. Then we have habitat, stream flow, rating curve. We have shown that it's possible, let's call it in the same way, this is stream flow. It's possible to obtain this curve. So we can have mathematically a function that is WA as a function of Q. So we can combine the two functions. WUA is a function of Q, which in turn is a function of time. So if we combine these two information, we actually can translate the stream flow time series into a weighted usable area time series, which is provided this curve doesn't change, provided the morphology doesn't change, of course, in the time span. But here, so we have how the habitat available has been changed in these 1, 2, 3, 4, 5, 6 years. So we can use this time series and analyze this time series quantitatively to understand which have been the most stressful events, for example, the events with the lowest habitat availability, or which have been the average available habitat over a given time span. Now suppose we want to abstract water from this stream. We can use this in a very in a predictive way. I want to abstract up to 3 cubic meters per second from this stream. So the stream flow time series will change. If the stream flow time series will change in the reach that is subject to water abstraction, also this time series will change. Maybe the average available habitat will reduce. And we can compare how much this reduction has been. And we can do this exercise in a, let's say, scenario building way, in a predictive way, at very with very low cost, because we can simulate what happens if we reduce the abstraction to 2 cubic meters per second, 1 cubic meter per second, and we see how much the habitat is changing in these different scenarios, or how much the duration, the continuous duration of the stress event for the fauna is changing if we change the rate of abstraction. So this is the main concept. Just some visualization of what I just said. These are the habitat time series for 1 year, 2007, for a stream, for in the reference conditions, so conditions without our abstraction. And this is the average habitat available. These are altered conditions. So we have an abstraction, and the corresponding habitat time series changes. So if we choose any threshold, like the red line, we see below which we can consider stress events. We have that under reference condition, the duration of a continuous stress event is 30 days.
Is it a percentile of 3%?
Sorry?
The red line and the threshold.
Well, there are different ways to choose the threshold. In this case, is the area related to the discharge value that has the 97% probability of exceedance, so it's a representative of the low flow condition, let's say. But
3% percentile of low flow.
Yeah, so it's quite a low value, and we consider flows below this value to have to cause stress for the fauna. So in this way, there is a stress that is probably tolerable. But here, the duration of the stress goes up to 3 months. So maybe this is too much. So we don't have time to enter the detail of how to statistically analyze these curves, this variability in the duration of the stress events. So I will skip the next slides because they take some conceptual time, and maybe we can discuss it afterwards. But basically, you can build statistical curves that express the cumulative continuous duration below a certain threshold and how they change between the reference and an altered state. And you can play simulating these conditions. And you end up, the method proposes to develop an overall index of the habitat integrity that is the minimum between 2 indices. One, AGS is again in Italian, but is stress days alteration. So it expresses how much the stress days, the duration of stressful events has been changing. And it's called index of temporal habitat availability because it refers to the duration of stress condition. And then there is an index of spatial habitat availability that is basically the average available habitat over a given period of time. And you use the minimum of the two to build the integrity index. There could be other ways to build indices. But then you can end up with a, let's say, quite standard classification from very high to very bad habitat conditions that could be used to assess impact, to plan for inflows, or to assess or to design conservation measures as management application. But I will not go further into this. The final slides, you will see some references. It's mainly from, this is mainly from the national, how this method has been entered into the national Italian legislation to assess inflows. All these operations, the statistical analysis of combining hydro-morphology with a biological model and then doing this operation, which are quite complex, are provided into softwares that are plugins of the QGIS software, so they're free to use, provided you have the training to handle them. And so the group that in Italy has been working on this has created this plugin which is useful to help mapping in the field. It's called MapStream, and CStream, which is useful to do the analysis so that this could be used even by non-researchers or so for a broader application. And yeah, I think that's it.